made it, found their way back to the school. All right, so I left off and I was teasing this idea that maybe we could get voters to vote on paper, not know anything about crypto, not use computers, and still somehow we could get an encryption of their vote and kind of feed it into the back end of the system. So the first ballot that achieves this, and this is still a very good ballot, one of the best options, is called pret-a-vote. You have candidates and they're shuffled. You split the ballot. You throw away the shuffling of the candidates. Now you have a privacy-preserving receipt. Now there's two issues with this ballot. Okay, the first issue is, how do you know what's printed in the QR actually corresponds to like the right ciphertext beside the right name? So how do you know that like there's an encryption of Alice in the second spot in the QR code? And so the answer for the pret-a-vote people would be you can request any ballot to be audited. So they'll give you a ballot and then they'll say, okay, do you want to vote on it or do you want to audit it? And you might be like, I want to audit this one. So then you keep it. And then what they'll do is they'll open up the encryption for the whole ballot. So they've committed to it because they print it on a piece of paper, so they can't change it once it's printed. Then you can take it home and then you can check that the encryption is all right for all of the candidates. Okay. The other problem, or the other issue that you have to think a bit about, is who prints the ballot. Because the person who prints the ballot, they know what the permutation is for this particular serial number, and so they know how you voted later on. When they see this go on the website and they see that you marked the second candidate, they know that the second candidate was Alice because they were the ones that printed the ballot. So the trusted printer problem is basically not solved. There was some work on it. Alex Essex, for example, or Tal Moran. There's a few people who had some proposals for how you could have multiple printers, so each one prints kind of like pieces of the ballot. But in general, that's like one of those problems that in practice just kind of gets ignored. You assume that there's some trusted printer that can print these things. Okay, now there's another ballot that's very similar called PunchScan. So this was a system I worked on. And it's almost the same as pret-a-vote. Except for it's more complicated, as you can see. But it's based on the same principle. And it has one small fringe benefit that maybe you think is good or not. So let me explain the ballot first. So this is 2 layers of paper. Okay, here I have it split out. So there's a top layer. This square is meant to represent, I don't know if you can see my mouse. This square here is meant to represent a cutout. And same here. So these are like holes in the paper. And so when you put this piece of paper over top of this piece of paper, this is what you would see. And so you can see that there's symbols beside the name and they're shuffled, and every ballot has an independent shuffle. And then there's symbols down here. And once again, they're also shuffled and there's an independent shuffle. And so if I want to vote for Alice, for example, what I do is I actually take a bingo dauber, and it's kind of fun. And I color, the dauber is really big. So when I go to mark the Y here, it actually gets ink on both sheets of paper. Okay. Then when I separate it, you can't really see it in the picture, but there's like kind of like a ring of ink on the top. And in the bottom, you can see that it's also, there's ink in the bottom. So depending on whether you have the top or the bottom, you can see how the person voted, or which position, I should say, that they marked. Okay. And if you so then what you do is you separate them and you shred one of them, and it's your choice. So you choose at random. So let's say I decide to shred the top one. Then I can take the bottom one home after it's registered. So you scan it and then you take it home. And you can see I marked the second position. The second position has a Y beside it, but I don't have the symbols that were beside the names. So I don't know who Y corresponded to. It could have been beside Carol. It could have been beside Bob. It could have been beside Alice. So I have no way of knowing, if I show this ballot to someone else, they have no way of knowing that I voted for Alice. Conversely, if I keep the top half, you can see I marked the second position. You can see the symbols beside each name, but you don't know what symbol was underneath. Okay, and it could have been any permutation of the symbols, so it could have been this could have been a vote for any of the candidates. Okay, so it's basically the same principle as pret-a-vote, except for you have kind of a double permutation. And the main benefit of this is you automatically, when you keep half of it, you get to audit that these symbols were printed correctly. Or you could audit that these symbols are printed correctly. So in Prêt-à-Voter, you have to explicitly ask for a ballot to be audited, and most voters aren't going to do that, right? So maybe like, I don't know, 1% of ballots get audited or something like this. But in PunchScan, half of the ballot gets audited half of the time. Or sorry, all of the time. Half of the ballot gets audited all the time. And so if you start misprinting ballots, you're going to get caught pretty quickly, with exponential likelihood in this system. So anyways, it enhances the security, but as you can imagine, it was actually a usability nightmare. We did run an election. It was just a student election using the system, and yeah, it was. It's not the most usable system. Prêt-à-Voter is certainly much more useful. Okay, here's a completely different approach. So this is from Ron Rivest from RSA fame. And so in his scheme, it's called 3-ballot. What you do is you get like this 3-ballot, he calls it. So it's like a triple ballot. And the idea is if you want to vote for, say, Bob, you mark Bob in 2 of the 3 ballots. So I might mark Bob in the first 2. And then for every candidate that you don't want to vote for, you mark them in 1 of the candidates. You mark them on 1 of the ballots. Okay, so this is a properly formed 3-ballot. It corresponds to a vote for Bob because it's marked in 2 candidates, across 2 of the ballots. Then what you do is you destroy 2 of the 3 papers. So, or let me flip it around and say you choose to keep 1. So let's say I choose to keep the last one. What I'll do is I'll throw away these 2. I can shred them on the spot. Okay, there's, once again, all of these have like kind of like a serial number that matches to ciphertext. So I'm kind of skipping over that link, the link from the paper to the ciphertext now. I'm just focusing in on the usability aspect. But anyways, let's say I keep the third, portion of the 3-ballot. Then you can see that it looks like a vote for Alice, but I didn't actually vote for Alice, right? I actually voted for Bob, and this doesn't look like a vote for Bob. And so even if Bob was filled in, it could have been just because I have to put Bob somewhere. And so maybe it was on the ballot that I happened to choose. So this is privacy preserving because you can't tell from whether there's a mark beside a candidate's name or not, whether you actually voted for them, because all of the candidates have at least 1 mark beside their name, and all of the candidates have at least 1 empty spot beside their name. So 3-ballot's kind of nice. The main problem with it is it does leak statistical information. So if I were to choose one of these 3 to keep at random, then you would expect that if I voted for Bob, so given that I voted for Bob, that there would be a 2/3 chance that Bob would be filled in on the receipt that I chose at random. And for the other candidates, there would only be a 1/3 chance. And so anyways, you can do some math on it, and you can see that that you can start making educated guesses at how people voted based on their receipt. But there's always plausible deniability. You can't guarantee that someone voted a particular way. But anyways, that partial information I think scared people, and so there hasn't been any uptake really of 3-ballot. It's also it's a little weird. Like here, like Prêt-à-Voter, you just vote like normal, right? The only thing is you have to find the candidate, but then you just vote just like you would normally vote. Whereas here you have to explain to the voter, okay, only vote once for the candidates you don't want and stuff like that. And so it's maybe not the most usable system in addition to having the partial information leakage. Okay. Anyways, there's a whole bunch of systems. So I picked the 4 like kind of high running systems, but there's more than just this 4. But the final thing that I'll show you is Scantegrity. So this is another project that I worked on that was basically we learned a lot of lessons doing PunchScan, a lot of usability lessons. And so we tried to really refine it. And so the idea with Scantegrity is you have a ballot. It looks normal. The candidates are in the right order. Everything looks normal. But when you go to mark the candidate, let's say I want to vote for Alice, I use a special pen. And when I mark the area here, when I circle it in, there's in invisible ink, there's a code that appears. So like TKG, for example. So what I can do is I can write down TKG and I can take it home. Now, this doesn't prove to anyone that I voted for Alice as opposed to Bob, as opposed to Carol. Every candidate has a different code, and the code is different on every ballot. So you have no idea where TKG is going to show up across the election. And so the idea would be, I take the receipt home, I type in my ballot serial number, and then there's a website, and it will show the confirmation code. It will say, okay, for this ballot number, we recorded TKG. Okay, so we call this step cast as intended. So it doesn't prove that my vote counted for Alice. It just proves that at least it got my intention right. And then there's going to be some proof that's going to prove that, okay, TKG was mapped correctly to Alice and a vote was added for Alice for this ballot without revealing anything. And that's going to look a lot like kind of the mixed network example I gave, but the details are actually quite a bit different. So I'm not going to go and show you another completely different backend. You could adapt this to work with CGS or with a mixed network if you wanted it to. Okay. So anyway, so this was a real system. We actually developed it. We deployed it. We ran a real election in Tacoma Park. I have some pictures I'll show you. So everyone's curious about the invisible ink. That's probably the coolest part about it. So the lead on this project, he's a pretty well-known cryptographer named David Chom, and he got obsessed with invisible ink, and he would always go to UCLA, and there was a chemistry prof, and they would work on it. And it's this kind of weird area where a lot of secrecy agencies use invisible ink, or maybe they did earlier, in the 50s, 60s, and 70s. And so all the knowledge is kind of top secret, and there's these patents and stuff. And so it's sort of this obscure area. But anyways, they worked out several different formulations. We ended up using 4 different kinds of ink. So on a ballot, you have your normal ink, which is black. Then you have the invisible ink, which activates when you mark it. Then you have to have a dummy ink, which is the exact same color as the invisible ink. So you can't tell where the invisible ink ends and where it starts. So we call that dummy ink. And then we put this fluorescent ink over top, which you can see in the top right corner, that just sort of masked it. There was kind of random masking. So if you got in with a black light or something like that, and you're trying to figure out what these codes are, then it would sort of obscure it. The ballot allowed write-ins. This picture is actually from a mock election that we ran, and then this ballot's from the real election. But yeah, so we had just invisible ink printed where it didn't reveal anything, but when you marked it, it would be dark. And there's all sorts of problems when you run an election like this. It's incredibly complicated. It took us 2 years to do the whole thing from start to finish. Tons of grad students. I was a grad student at the time, and tons of professors, 5 professors, and 7 or 8 grad students working on it. And you have to sweat every detail when you do something for real. For example, the write-ins, you can see that the tip of the pen is a fine point, because when you write a name in, you want a fine tip marker. But when you swipe a code to vote for someone, you want a chisel tip. So we had pens that had a chisel tip on one end, and then it had a fine tip on the other end. Every small detail like that, you have to worry about it. There was lots of, so this is what the ballot ended up looking like. This is it when it was marked. And this is sort of the election setup. So we had these scanners, and so you just sort of drop the paper in to the scanner, and it would feed automatically through, and there was a laptop that would record the scan, and then it would end up in the ballot box. And yeah, anyways, very involved process, but it was a lot of fun. I'm really glad I got to be involved in that project. Now, back to the ballot. So what does Scantegrity have that these ones don't? And so I would say that there's 2 things. The first thing is it's very usable. Basically, if you don't care about crypto, you can just ignore the code. You can just vote it like you normally would. There's a code that appears there, but you just ignore it, and then you cast your ballot. So it's exactly the same as a normal optical scan voting system. Predavote is also very close, except for the shuffling of the candidates. That's the only main difference. But the other thing that this has that Predavote and the others don't have is it has very strong dispute resolution. So let me illustrate that with going back to Predavote. Let's say I go online and I type in my ballot serial number, and it says, oh, for you, I recorded that you marked the first position. and you're like, no, I voted, I marked the second position, right? You can't really, I mean, maybe if you have this physical piece of paper, they could look at it and be like, okay, that paper looks real. But it's really hard to prove that you actually marked the first position. Sorry, that you actually marked the second position when the website's telling you that you marked your first position. Okay, so dispute resolution is really hard. What's nice about Scantegrity is if I went on the website and it said, "Oh, we recorded XYZ for you," you actually know a proper confirmation code that was beside a different candidate, right? So let's say that XYG was beside Carol. If you voted for Carol, you would have learned XYG, but you wouldn't know anything about Alice's code. So you couldn't cough up the value TKG. So if you were just trying to dispute the election and like cast doubt on the results, maybe you actually voted for Carol and you got XYG and you're just like, oh, I didn't vote for Carol. Then the EA will say, okay, well, if you didn't vote for Carol, then tell us the code that you actually did vote for, right? And you wouldn't know what these other two codes are. Okay, so that's why the invisible ink has to be like kind of secure. So in the ballot box, we assume that the voter can't know what a code is unless if they actually reveal it. But if you're like, oh, I did TKG, then they would have to, there's this process, but basically they would be forced to decommit some information about your ballot, and everyone would see, oh, DKG was a valid code on that ballot. So now it looks like it was actually malfeasance, like the EA changed your vote. So anyway, Scantegrity gives you kind of stronger dispute resolution than the other ones, but otherwise they're all pretty good. And I would say that Scantegrity and Predivote are kind of the best of the two. Sorry, my scrolling's messed up again. They're kind of the state of the art for this. Okay, yeah, so Scantegrity, it uses a different backend. It has a trusted hardware assumption. Now, fancy people call it trusted execution environments. We didn't really have that back then, so we called it a black box assumption. But anyway, so you have that. And then the nice thing about Scantegrity is you don't actually need any fancy encryption. You don't use homomorphic encryption. You don't have to do anything. The only thing you need is a commitment function. So the ability to like say hash some data, post it, and then later open it up and reveal it. And so that construction of just using a hash doesn't work, by the way. You have to do something a little more involved. But anyways, you get the idea. So all you need to do is commitment. So I'm not going to walk through the back end of Scantegrity. I showed you one back end of a system. I think that's enough. But if you're interested in it, you can read the paper. And we have actually a simpler version. It's called ePerio. And it's as good. It does everything that Scantegrity does, but it's faster, but it's also like simpler conceptually, I think. It's a conceptually simpler thing. So if you're interested in the back end, I would point you to that paper as opposed to the original Scantegrity paper. But that's up to you. Okay, so these are your sort of human votable options. And so if you put one of these together with the back end of a system, then you have a proper end-to-end encrypted, end-to-end verifiable voting system. Okay, so I'm going to shift gears now, and for the last 45 minutes or so, I want to talk about internet voting. So internet voting is a little bit different than voting in person. So all of these systems have assumed that you get your ballot, you're actually identified in person, and the most important thing is that you vote in a secret ballot booth. So when you're filling your ballot out, nobody's looking behind your shoulder. Nobody knows how you actually voted. Now you can throw doubt on that assumption as well. So there's a nice paper from Josh Benelo where he argues, well, because you can have like cameras in your glasses and you can have cell phones and things like that, maybe we shouldn't assume that you can vote in private anyways, because you could just record yourself voting. But that's another assumption that all voting papers make, is that they're coercion resistant sort of by definition, because nobody can see how you actually vote in the ballot booth. Now, when you move to an online setting, that assumption has to go away. So if I'm voting for my computer, I'm at home. Anybody could be beside me, watching me, telling me how to vote. They could be threatening me to vote a particular way. They could be paying me to vote a particular way. And they don't even have to like kind of be there making me vote. What they could do is they could just vote for me. So somehow I need to have some sort of authentication. I need to have a password or something like that. And so it's not like I have to be the one that types the vote in and they're on my shoulder telling me what to do. It's like sufficient if I just give that credential to them and then they just vote on my behalf. So coercion is this sort of new problem that emerges in the internet setting. And it's the problem that I'm going to talk about. So I'm going to show you a scheme called JCJ that was one of the earliest ones to solve this particular problem. There's another problem that you have, and that is how do you know that your computer is doing what you want it to do, right? So you ask for an encryption of Alice. How do you know that it actually encrypts Alice? Okay, so there is one like way of doing it it's not fully sufficient, but it at least goes partway there. So I mentioned before there's a system called Helios. And so Helios is an online internet voting system that doesn't try to solve this particular problem. Okay, it just doesn't attempt to. And I'll show you what it does for the untrusted platform problem, but it's basically a robust solution, but it's better than doing nothing. So it's actually an earlier idea due to Josh Benelo. So it's called the Benelo Challenge. It's really simple. So basically what you do is you tell your computer, I want to vote for Alice. And so it encrypts, oops. So this is your computer. And so it produces an encryption of Alice for you. And then you say, actually, either go ahead and cast that. Okay, so I believe that that's an encryption of Alice, or I want you to open that up. Okay, and if it opens it up, then it's going to show you the randomness that it used to create the encryption of Alice. And then I don't know what you do with it. I mean, if you can do AlgaML in your head, you could say, oh, that's wrong. You could ask your computer whether it's wrong, but if it's lying to you about encrypting things, it can also lie to you about whether it validated or not. You can use a secondary device. So if you have a phone maybe, and you have an assumption that at least one of your two devices isn't. And I should mention too, it's not like the untrusted platform. I'm not talking about like Microsoft like corrupting ballots because you're running Windows, right? Like that is possible, but that's like a really far-fetched threat model. We're basically just talking about malware. So lots of computers get malware. And we've seen malware that steals your banking credentials, and it's conceivable that it would steal your voting credentials or try and mess around if it knew that an entire country was running a certain software in order to vote, like say in an election. You could certainly imagine, like in the US, say a presidential election in the US, that's pretty high profile. If everyone's using the same software across the country, you could see some of these APT groups, maybe design malware specifically to try and influence votes. So I don't think it's a very unrealistic assumption to make. But anyway, so the Benelo challenge kind of works in this case. It's probably not fully sufficient. You'd have to have like a secondary device or something like that. The other thing that you can do, so when we ran Tacoma Park, when we ran the election with Scantegrity, we also had to have a remote voting component because some of the voters were not in Tacoma Park. And so we have another system, I'm not going to talk about it, called Remotegrity. But basically the idea there was that we assumed that we could at least mail something to the voters. And so if you mail the voters a ballot, and beside every name, think of it not in invisible ink, but just in normal ink, there's a code. And when you vote, you type in the code as opposed to typing in the name of the candidate that you want to vote for. So instead of voting for Alice, I would just say, hey, I want to vote for TKG. Now my computer has no idea who TKG corresponds to. So if my computer wants to flip my vote from Alice to Bob, it doesn't know that TKG is a vote for Alice. It just knows it's one of the codes that are on the ballot. and it doesn't know what code is beside the other candidate's name, so it can't like meaningfully flip my vote. So that approach is called code voting. We didn't invent it in remote integrity. It was invented by David Chom, and he had a system called SureVote. I think that was the earliest thing. Although David was involved in remote integrity as well. So I'll just put SureVote here. And there's been, there's maybe a dozen papers or so on how to do code voting schemes and different properties that they have and things like that. So this is sort of an interesting problem that doesn't get a lot of attention. Probably getting a lot more attention is the coercion resistant problem. Now, before I go there, I'll just mention the other problem with internet voting is denial of service. So if you can't reach the voting system, or if someone's trying to stop your ballot and dropping your ballot as you try and transmit it or something like that, that's also a difficult problem. Usually people in crypto don't worry about it. They just consider it a network problem. And so we assume the network layer is somehow going to, take care of this for us. So I've never seen a paper that actually tries to address this issue. It's just assumed that someone else is going to do that. Okay. All right. So let's do a deep dive on coercion resistance. So I'll show you the first scheme that sort of did something like fairly meaningful on it. So it's called JCJ. So Jules Catalano and Jacobson. It was at WPES. There's also a paper called Civitas that was at Oakland, and it was basically an implementation of JCJ. There were a few tweaks, and they did some formal language kinds of stuff as well. And so I think one of the authors might even be here, because I think I saw him on Twitter asking about this talk. But anyways, so JCJ and Civitas implement the same basic mechanism. The principle that underlies it is relatively simple, even if the crypto isn't. So the idea is that voters somehow are going to have a credential. So a credential we'll think of as a key. So it's like, I know the private key that corresponds to a public key. It doesn't have to be in that form, but anyways, that's a form that works pretty nicely. And so they have this credential and it's real, okay? And if someone comes to you and says, hey, I want you to vote a certain way, or I'll pay you to vote a certain way, the idea is to let the voter make up a fake credential. So they can just make up a fake key, and the crypto has to be like, it has to be designed in such a way that they can convince the adversary that the fake credential is real, or at least it's indistinguishable from a real credential. Okay, so first off, if you just make up a key, it looks like it could be a real key. You can't tell the difference between a real key and a fake key. Okay, but the real key needs to be like somehow involved in the cryptographic protocol. Otherwise, the voting system isn't doing what it's supposed to. So everywhere you go and you use the real key, it has to look the same. Like the election officials have to go and use the fake key in the exact same way, or whatever proofs you get about the real key, you have to be able to simulate them for the fake key and things like that. So it's a bit of work for the voter in order to do it, but it is possible to do. Okay. Then the other hard part about this is we need to change the backend. So it can be like a CGS style system, but we need to get rid of the fake votes before they make it into the final tally. And we got to do that in a way so that we assume that nobody knows which ones are real and which ones are fake. Okay. So that's the other challenge for it. Okay. So let's start with, so in internet voting, it's usually the case, like if you do in-person voting, you don't really think about the phase that happens before people show up and vote. You start your protocol when voters are showing up to vote, you show them what the ballot is and things like that. But inherently, before people vote, there has to be some sort of registration phase. So people come in, and in most voting systems, it's easy. There's no crypto involved. It's just, you have a list of eligible voters, and then people show up, they have a driver's license or passport or something like that, and you cross them off the list. Okay, so that's how most systems work. In order to deal with the coercion problem, what we're going to do is we're going to start doing the crypto earlier in the system. So we're going to actually start it at the registration phase. So what we're going to do is we're going to build a kind of So you have a voter roll or roster. And so we're going to start building a cryptographic version of the voter roster. Okay, so let's assume we have an election. We just have 3 voters to keep it simple, A, B, and C. I would call them Alice, Bob, and Carol, but I'm going to keep that for the candidates. So you're either going to vote for Alice, Bob, or Carol. So these are just voters A, B, and C. And what we want is, we want for every voter, we want them to have a public key. Okay, so you can think of it as a credential. It doesn't even matter that it's a public key, I don't think, unless if you want to go into the details of the proof itself. So I'll call it a public key. It could also just be like a password or something like that. So some of our later work, we played around with this protocol to try and improve it, and we use passwords instead. But generally, if you're thinking at crypto level, it's usually G to the power of whatever your credential is. Okay, so you have some secret, and it's going to be G to the power of your secret. Sorry, my software again is glitching. Okay, I'm just going to try and forget about writing it. Okay, so you have these credentials, and they're wrapped in encryption. Okay, so we can, once again, we can use exponential LGML. We introduced it earlier, so let's just use it. And it's going to be exactly the same as we assumed before. There's going to be a threshold assumption. There's going to be an election authority that's able to decrypt these, but there's going to be 5 of them, and you need 3 of them to agree. And if at least 3 of them are honest, then they're not going to decrypt anything that they're not supposed to. And one of the things they're not supposed to is ever decrypt this voting roster, at least in its kind of raw format here. Okay, so we're going to assume that these things stay encrypted. Okay, now what happens here is in the original JCJ proposal is this is given to you. So someone else chooses it, like the election officials, and they give it to you. In later work, like my own work, we let the voters choose. But let's just roll with the idea that someone else is going to choose it for you. It doesn't really change much. Okay, so what will happen is you're voter B, you'll show up, and show up doesn't actually mean anything. We're going to assume that you connect through the internet, right? So you connect to the server and you say, okay, I'm ready to register. So they do whatever, they check whatever they have to check, and they agree that you're going to get added to the roster. So then what they do is they create this credential for you. You can also do this in a threshold manner. So the 5 trustees can all create shares, and then you can combine them, but I'll just describe it as if it's one. And then they encrypt it. Okay. Now I have no idea whether they encrypted this value or not. I don't know. So what they're going to do is they're going to give it to me. Okay, so they're going to say, this is an encryption. This is what's inside this encryption. Now they could tell me how to encrypt it. They could give me the randomness that's used to encrypt it in order to encrypt it here. But because I want coercion resistance, this is going to be my real credential, and I want the ability to make up a value here. Okay, I'm going to make up a completely different value. And I'm going to go around telling everyone that actually what's on the roster here is an encryption of a completely different value. Okay, so if the EA tells me how to encrypt this in order to get this ciphertext, then I can't make that credential up, because then people will say, well, tell me what the EA told you about how to encrypt this to give it to this. And if the numbers don't work out, then I'm not going to believe you. Okay, so what we need from the EA is we need something that's more, that can be malleable a bit. Okay, and so what they're going to do is they're going to give you kind of a funny looking proof, but the logic behind it is actually really cool. Okay, so they're going to give you a proof that they're going to prove in zero knowledge that either one of these 2 statements is true. Okay, so either it's the case that this value, this ciphertext decrypts to this value, the value that I told you. Okay. Or we're going to assume that voters have some public key, not the public key that's being registered here, but some other public key that is tied to their identity. Okay, they're going to say, so the EA knows what this public key is, and so they're going to say either this is an encryption of this value, or I know your private key, the private key that corresponds to your public key. Okay, so this probably sounds a little bit odd. So what's the logic behind this? Well, if you're the voter and you receive this proof, okay, you know this isn't true because it's your private key. You're the only one that has it. So you assume that this has to be true. One of the two things is true. You know this isn't true, so therefore it must be the case that this is true. Okay? That's you as a voter receiving this. Now, let's say you're the person coercing the voter. So you coerce the voter and you say, hey, voter, what was the proof that the EA gave you? And so they give you this proof. Now, me as the coercer, I'm looking at this proof and I have, I don't know whether this is true or this is true because it's possible that this is true. The person giving me the proof, the voter, the person I'm coercing, does know their own private key. Okay, so they could have created this proof themselves, or maybe it's the case that they're not lying about what value is encrypted. Okay, so what that allows you to do is it allows you to make up a fake credential as a voter, and you can make up a fake proof that this credential is encrypted inside this ciphertext. But the way you make it up is because you use your private key in this clause. So you basically issue a proof where this is true and this isn't true. The fake proof looks identical to the real proofs. In zero knowledge proof, they have this property, we call it witness hiding, which means that you don't know which clause is true in an OR proof. So you know one of the two is true, but you don't know which of the two it is. Okay. And so anyway, so if you put all of this together, you can basically make a fake credential and you can make a fake proof as well. So this style of proof is called designated verifier proofs. And once again, it was sort of invented by the same people who invented the voting scheme, a different subset of authors. Let me write it here. And it's pretty cool. You can do signatures with it. So if you have a signature that you only want one person to verify it, you could be like, okay, this is a signature on this message, or I know your private key. Then you give it to the person. They know that it must be a valid signature. Otherwise, because they know that you don't know the private key. But if they try and show it to someone else, then nobody knows whether it's a valid signature or the person's making it up because they do know their own private key. Okay. So anyway, the logic is kind of, I don't know, mind bending or whatever, but once you get used to it, it's pretty cool. So yeah, so these are called DV proofs or designated verifier proofs. Okay, so at the end of registration, basically what we do is we have a real credential. We're very convinced about what our real credential is. And we can also make up fake credentials and fake proofs that our fake credentials are real, even though they're not. And everything's indistinguishable. The adversary has no idea whether you're giving them the real credential and the real proof, or they're giving you the fake credential and the fake proof. They can't tell them apart, even if you record all of the information. Okay, so that's registration. Okay, now it's voting time. So what's going to happen is people are going to show up, they're going to cast their vote, and they're basically going to submit 3 values. Okay, so this is going to correspond to 3 people voting. So one person shows up, they vote for Alice, and they submit a fake credential. Okay, a credential that's fake. The second person shows up, they vote for Bob, and they submit a real credential. And then the third person shows up and they submit a real credential as well. Okay, so these credentials correspond to, if I can pull this up, I'll show you. Okay, sorry about that. So anyway, so voter B is using their real credential in voting. Voter C is using their real credential in voting. And voter B is also lying about their credential. And voter A is, in this election, we'll assume doesn't show up, it doesn't vote. Okay. The other thing I could say is that the fact that I subnoted this B, but fake credentials are just fake credentials. There's nothing that like really ties this credential to the real B credential. It's a fake credential. Maybe the voter, made a fake proof that corresponded it to B, but there's nothing about this that like corresponds to B as opposed to any other credentials. Anyways, if you didn't get that, it doesn't matter. Let's just move on. Okay, so we have 3 votes, 1 fake vote, 2 real votes. Now, the first thing we want to do is we want to make sure that people aren't copying each other's votes, right? So for example, I could copy this credential, post it as my own, and then change the vote. And so we don't want that. Or I could be like, oh, this person, I don't know who the first person voted for, but whoever they voted for, I'll vote for the same person. So I just copy their ciphertext down here. Okay. So what we do is we have a very simple zero knowledge proof, which basically says, hey, I know how to decrypt this I'm not going to tell you what it decrypts to, but I know how to decrypt it. And I know how to decrypt this as well. Okay. And so you do that for all 3 of them. So you assume that there's a proof of knowledge of what's inside these ciphertexts. Okay. Now you might ask, well, what stops you from replaying the whole tuple? Like I could replay this, and replay the exact same proof. The answer is nothing. So it's true. You could do that. So we'll assume that if you see something that's the same all the way across, then you're just going to ignore it. But otherwise, you'll accept it. Okay. So now we have our votes. And so now we're ready to tally. So at the tally stage, basically we want to count this vote. We want to count this vote. And we don't want to count this first one. Okay, so we want to filter it out. Now, let's say we do some processing on it or whatever, and we realize that this is fake, and then we want to cross it off the list. Remember, the adversary, like say I was standing over your shoulder telling you to vote, I see that this is added to the bulletin board in the first position. Okay, so I know this is the ballot that I asked you to vote for. Okay, so I'm going to watch this ballot. Okay, so I can watch it all the way through the proof. Okay, so you can't just cross it off the list. Okay, you're going to have to do something to try and hide which ballot it is that you're eliminating. So the thing that you'll do, we already saw in the first half, which is shuffling. Okay, so what we're going to do is we're going to use a verifiable shuffle to shuffle these things up before we start crossing things off the list. All right, so I'll show you how it works. And what we're going to do is there's one small step that has to do with people submitting more than one vote. I'm just skipping it. The process is basically exactly the same. So you can see the paper for how to do that. But what I'm going to do is I'm going to take the votes. So I checked the zero knowledge proofs already. Okay, so I checked these proofs. So I'm assuming that everything is well formed. So I'm just going to take these 2 values, the thing that the person's voting for and the encryption of their credential. And I'm going to shuffle them up. So now they're in a different order than when they came in. Okay. Then what I'm going to do is I'm going to take the roster, and I'm also going to shuffle it up. So these are the real credentials according to the roster. Okay, in a different order. So we have the real A, the real B, and the real C, and then here we have the votes as submitted. Okay. Now what I want to do is I want to figure out, is there a match? So this credential, does it match any of these roster entries? Okay. And so it'd be really nice if I had a way of, let's say, looking at 2 ciphertexts and trying to decide whether they encrypt the same value or they encrypt different values. Okay. So this is a technique that was developed in order to make this happen. Okay. So there's this thing called a plain text equality test, and it's one of the contributions of the JCJ paper. So what you're going to do is actually, okay, forget about the details. Let's just think at a high level. Let's assume that you have a black box and it will do it for you. Okay. So what you're going to do is you're going to compare this, and it's not going to be the same. You're going to compare this to this. It is the same. You could actually stop at that point, but for completeness, you might compare it to this and then decide that that one's not the same. Okay. And you're going to do that with all of the ballots. Okay. So all the ballots you receive, you're going to compare it to every single roster entry. If you get a true for one of the rows, that means it's a valid vote. Here, this matched at least one of the credentials, so it's valid. This was the one with the fake credential. The fake credential doesn't match any of the things on the roster. And so at this point, we can reject it. We can reject it by literally scratching it off the list. And the reason that doesn't reveal any information is because we shuffled the list first. So I don't know which vote. I know one vote got eliminated, but I don't know which one it was. It could have been any of the 3. So it doesn't tell me anything about it. Okay. then just ignore this for now. But then what I can do is I can simply decrypt the candidates. So I see that Alice got 1 vote and Bob got 1 vote. And so in this case, it's a tie. But I'm done. Okay, so the last little piece that we need to understand is how do I do this test? I have 2 ElgaML, let's assume they're exponential ElgaML ciphertexts, and I just want to know, are these the same value or not? Okay, so there's a protocol that's proposed called plain text equality test. I know that Vanessa is going to spend some time tomorrow talking about it because there's some technicalities and a nice like little breach that can happen, and it doesn't work maybe as cleanly as you might expect. But what I'll do is I'll just give you the intuition so that you're ready for her talk tomorrow. Okay, so here's the problem without all the details of the voting system. So I have an encryption of A, exponential ElgaML. I have encryption of B, exponential ElgaML. I want to know whether A equals B. And I'm going to assume that the person doing this test, they have the power to just decrypt A and B. Okay, so they have the private key. It's like a threshold scheme, 3 out of 5 or whatever. And they're capable of actually decrypting it. So the simplest thing they could do is they could actually just literally decrypt A, they could decrypt B, and then they're certainly going to learn whether A is the same as B or not, okay? But what we want in this test is we want them to learn precisely whether these 2 things are valid, are equivalent rather, and nothing else. So we want it kind of like a zero knowledge property, okay? Now you might say, well, why is this not a zero knowledge proof? What's the difference? So in a zero knowledge proof, the person who's doing the proving, they know what the answer is. So I can give you a zero knowledge proof that 2 values are the same because I know what those 2 values are, okay? This is a little different because the people that are doing it don't actually know what the answer is until they do it, okay? So that's why it's a test, not a proof. So in a proof, the person who knows the secret, the witness, they're the ones doing it. And in a test, somebody else who has the power of decryption is doing it, but they actually don't know what the answer is themselves until they do it, okay? So is there a way that they can decrypt these 2 things without learning anything other than whether they're the same or not, okay? So the intuition of the test is actually relatively simple. Because this is additively homomorphic, what we can do is we can start by subtracting the 2 values under encryption, okay? So we take the encryption of A and we subtract off B, and so we get the encryption of A minus B, okay? Now, if A and B are the same value, that's going to be an encryption of 0. And if they're not the same value, it's going to be an encryption of whatever the difference is between these 2 values. So I'm just going to call it delta for difference, okay? So you either get an encryption of 0 or you get an encryption of some other number, okay? Now at this point, you could just decrypt. So you could say, okay, let's decrypt this and we'll see. Let's see if it's 0 or if it's non-zero. If it's 0, we'll say that they're the same. And if it's non-zero, then we'll say they're not the same. The only problem with that is that this delta does leak some information, okay? So you know the difference between these 2 values. You don't learn necessarily what A is and what B is, but you do learn the difference between them, and that's some partial information, and we don't want to leak even any partial information, okay? So then what we can do at the next step is we can blind the values. So what the trustees do is they actually take turns. So they're all going to do this. So the first one's going to go, they're going to take some R value and they're going to multiply it in. Okay, they'll have to issue a zero knowledge proof that they know the value that they multiplied in so that they don't just replace this with a completely different ciphertext. So I actually took this ciphertext, I put an R value in, and this is the output. And so what happens is when you put an R value in, it ends up being multiplied. So you get 0 times R or delta minus times R, depending on which case you're in. 0 times anything is always 0, so that's fine. And delta times R is usually always never 0 and something else, some non-zero value. And furthermore, if you multiply a bunch of R values in, you lose track of what delta is. Okay, so there's, for this output here, there is some R that would turn any delta into this R. I didn't say that very well, but anyways, this is information theoretically hiding. So it completely, it's like a one-time pad. So basically you multiply in a one-time pad. And so what ends up happening is you get this completely random value. Doesn't tell you anything about delta, which is the difference between these two values. So you don't learn A, you don't learn B, you don't learn the difference between them. You just learn that it was some random number. And that tells you that they were not the same number in the first place. Okay, so at this point, you can decrypt this, and then you can decide whether they're true or not. Okay, so that lets you fill in this table. And when you fill in the table, then you can cross off the fake ballots, and then you can form your tally. Now, what's the problem with this scheme? It's actually a really nice scheme. Basically, the only problem with it is it's super expensive, right? It's quadratic in the number, well, the number of votes times the number of entries on your roster. And the other thing about it is anybody can show up and they can submit one of these things. So if I want to submit 1 million fake ballots, I can do it. And then the EA has to do, 1 million squared, like kind of work in order to like clean this whole table up. So you can think of that as an attack called a board flooding attack, where you just flood it with a bunch of fake ballots because it's quadratic and it's going to take a long time for the EA to process it all. And even though we're talking in theory, the numbers do get big enough in practice. So you could flood it with thousands of ballots, and it could take a couple of days in order to comb through it. Okay, so it's not just like a theoretical thing. It actually translates into practice as well. Okay, so following up this, there's not a lot of research, but I'd say it's fairly substantial. I think there's about 10 significant or material papers that try and look at, is there some way to make this linear? So one of them is from us. So we also use panic passwords instead of using these like keys and designated verifier proofs and stuff like that. So we make a bunch of tweaks to the system. There's another nice system. This is a more recent one. There was a nice paper at CCS, a few years ago on algebraic max. So they're like max, but they have algebraic properties. So they work in like a discrete log. And the basic idea is that real credentials will have a proper MAC. And if you make credentials up, they'll have a fake MAC. And so you do a bunch of processing and then you try and see whether the MAC holds or not. And if it doesn't, you throw it away. And so it's also a linear time system. So anyway, these are two kind of extensions to this. And there's others as well. I just highlighted these two because I think they're nice. Okay, so that's it for me actually for today. So Vanessa will be here tomorrow and she's going to tell you a bit about how these things break in practice. I believe she has a keynote at SAC as well. So she'll go through probably a deeper dive on some of the protocols and then really try and catch her keynote, and she'll show you how some of this stuff breaks in practice. And I think she'll also tell you about some of the real world experiences that she's had, like running these systems in Australia and other places as well. So anyways, I thank you very much, and I hope this was useful to you, and hopefully you got all the details, and I'm certainly happy to answer any questions that you have. Thanks.